Hello guys, welcome to the second part of lecture 2. So we're gonna continue chapter 1, and now we go to the real work. We'll start logic gates now. So basically, the first start in any logic gate or digital design course is the basic or the three basic functions or logic operations that we can do to binary variables. Okay, so basically, what are the digital variables or binary variables? Binary variables are a variable that can take only two values. Okay, 0 or 1, high or low. Okay, so basically, this is a digital variable. So the basic three operations that we can do, or the functions that we can do using digital variables or binary variables are and, or, and not. Okay, these are three basic mathematical definitions. Maybe they have been introduced centuries ago, maybe 200 or 300 years ago. Okay, to represent some of the logic that human can do. Okay, so basically we are saying, for example, we are saying for and, the first one here, and we are saying that if you have two conditions, okay, and these conditions have either is satisfied or not satisfied, and there is another operation that depend on these two conditions, then you will not execute that operation until both conditions are satisfied. Okay, we refer to satisfied as 1, and we refer to not satisfied as 0. Okay, sometimes they call it true or false, true or false. Okay, but the two we just need two symbols. So the basic and the most convenient symbol to use are zeros and ones. Okay, even in decimal, by the way, the most convenient numbers to deal with are 0 and 1. Okay, so let's see here. So this is the first function and. Okay, and here is x and y, and the symbol for and is either a dot like this or a period, or you don't do anything. I mean, you just put the two symbols together. So you can write this in that way as well, x and y, and that's it. Okay, so basically in the first combination here, when x is not satisfied and y is not satisfied, then don't do this operation. Okay, so the output is 0. And if x is not satisfied but y satisfied, still don't do this operation. Okay, if x is satisfied and y is not satisfied, again don't do this operation until we reach the final value or the final possible combination that x and y can take, which is 1, 1, which means true and true, or x condition is satisfied, y condition is satisfied, then do the operation. Then the output here is 1. Okay, so basically, since each variable can have only two values, okay, so dependent on the number of variables that you have in your function, you can just trace all possible combinations and the output or y or the function in all in all these combinations. So here we have two variables. So we have two variables, x and y. Each variable has two values, which is 0 or 1. So the possible combinations that you have is 4. So the possible combinations are 4. 0, 0, 0, 1, 1, 0, 1, 1. And you can just do it. There is a mathematical, equation for it. So all possible combinations are 2 to the power of 2. Okay, 2 to the power of 2. Basically, these two here are the values that each variable can take. So 0 and 1. So we have two options, 0 and 1. So we have 2. And this is the number of variables. Which is 2 in that case. So if you have 3 variables as inputs or 3 inputs, then you will have 8 combinations and so on. 2 to the power of 3, which is 8. If you have 4, you have 16, and so on. Okay. And we call this, table here, we call it the truth table. So this is the truth table, truth table, which gives you the truth, or the behavior of the output based on all the possible combinations of the input. Okay. The second most important operation we will deal with all the time is OR. Okay, it's called OR. And from the definition again, in AND, both conditions should be satisfied in order to do the operation. Here, it's another logic that human can do, that you can do or do something if only one condition is satisfied. So if you have another operation, whatever it is, and this operation has 2 conditions or 2 inputs, we can say, then if any of them is satisfied, you can just do it. Okay, so we are saying here if x is 0 and y of 0, which means both conditions are not satisfied, don't do the operation. Then in the other cases, we have at least one of them is satisfied, or 2 in the last case, so do the operation. Okay, so this is the truth table for the OR. The last operation we have is NOT, or the complement. Let's do it, or complement, or the flip. Okay, basically this is very simple function. It has only one input and one output. Okay, and it just negates what we have in the input. If you have in the input 0, it will negate it. It will make it 1. It will complement it. It will make it 1. It will flip it. It will make it 1. If it is 1 at the input, it will again negate, flip, invert, and make it, or complement, and make it 0. 0, we have 1. 1, we have 0. The symbol for the OR is just like the plus sign, but it's not an addition. We will deal with arithmetic addition in the future, in this course, near future. But this is not, the regular, plus sign. I mean, it will not have the same meaning as a plus sign. So here this is a symbol for the OR operation. Okay, and basically here this is the difference. One, if it was an arithmetic operation, 1 plus 1 is 2, not 1, right? But here it's OR. 1 or 1 equal to 1. So in that case here, 1 or 1 equal to 1. This is OR, not plus, not arithmetic plus. And for the complement or the NOT, there are many symbols for it. All the time in this course, I will use another symbol rather than this. So you can use the prime like this. You can use just, just simple, line like this, slope with a slope. Or you can do like me, and I prefer so to put a bar, above the symbol, because this is, very clear. Okay. And again, for the AND, the symbol is a dot, or you just don't put anything. Okay. And here are the symbols for such gates. Okay. This is the symbol for the AND. It's like a box with around edges on one end. Here is a symbol for the OR, and here is a symbol for the NOT. Okay, these are the 3 symbols for our 3 basic operations. Now let's examine what's the true nature of these 0 and 1 and these logic gates. Okay, so let's make the question another way. What's inside these boxes? Okay. By the way, till this moment, this is all math. I mean, this truth table here for the three function maybe proposed maybe 200 years ago or something. Okay. So what is this in our context as computer or electrical engineers? So let's see our interpretation for it. So basically, we are dealing with computers, okay? And again, as I said, it's easier to deal with a computer with something at its opposite, like there is a charge, there is no charge, high voltage, low voltage, all such stuff, okay? So basically, 1 or 0 are representing two opposite, phenomena, either low voltage or high voltage. Okay, so basically the computer is just some circuit. There is some circuit inside this computer. These circuits, which are digital circuits, use two distinct input voltages, either low or high. So this is one example in the book, in Manu's book here, that you can represent all voltages less than or equal to 1. Any voltage here less than or equal to 1 as low voltage, or 0. We will give a symbol for such case, which is 0. And all voltages larger than or equal to 2 as 1, or high voltage. Okay. Here it doesn't necessary to have a limit, but we put this limit because basically any circuit has some limit in the input voltage, otherwise there will be a very high current and it may break, right? May burn. So that's basically the meaning of 0 and 1. It's at the end is just some voltage that you put in your circuit. How about the logic gates themselves? These boxes are actually circuits as well. Okay, and here is one example for the NOT circuit or the inverter circuit that makes the complement. Okay, very simple transistor, NPN transistor. By the way, you don't need to understand the details of this. I will just highlight it. Okay, it has one input, as you see here. This is the input, and here is the output from that node here. Okay, so if you guys recall the operation of the transistor when it works in the BJT transistor, when it works in saturation region, okay, if you put here a very high voltage, something like VCC, and VCC is the highest voltage in the circuit. This is the highest voltage in the circuit, or the whole board, the whole motherboard, for example, for a computer. So basically, if you put a voltage equal to that voltage, that's basically high, just something like this 3. Okay, if you remember the output here, the voltage at the output V will be equal to 0.2, around 0.2 or 0.3 or 0.1 or maybe less, something very small. So basically, when we put a high voltage, which is 1, we get here a low voltage, or as a symbol 0. And if you recall again, if you put here, a ground, if you connect this point to the ground, let's do it with another color. If you connect A to the ground, this will be cut off. In the cutoff region, the current will be 0. And the voltage here, VO, will be equal to VCC. Why? Because there is no current, so the voltage difference on the resistor here is 0. VR2 is 0. So basically, the voltage here is equal to the voltage here because the voltage difference is 0. Okay. If there is a voltage difference, there will be a current. So now, when you put 0 here, or low voltage, we get high here, high voltage, or 1. So in our circuits, instead of drawing all such stuff, resistors, transistor, and stuff, okay, we just put a symbol here, which is this triangle with the circle in the front, and this is the inverter. So whenever you see this symbol, you should know that this is basically a circuit, a digital circuit, which makes the operation of the AND. Whenever you see 0 and 1, you should imagine all the time that this is actually voltages, 0 and 1. Okay? When I put here VCC at A, that means I just connect this point to VCC. When I put 0 here at A, that means I just connect this point A to the ground. Okay? So this is basically what you should imagine all the time. Okay. Since we are dealing with, or we know now that these are actually signals, voltages, okay, we should also imagine the situation when you have, a stream of inputs, a stream of input data that goes into your circuit, goes to your inverter, or goes to your, AND or circuit. What it should be look like. So if we get this here, like this. So basically A, the voltage A, or the transistor input A, it's just a signal. This signal has two distinct voltages, either high, VCC, or low, 0, something like this. Or this, if the circuit has two inputs, A and B, or X and Y. Okay? So let's deal with a stream of input data. It's also easy. It's not hard at all. You have just mark the transition points in which the input changes from high to low or from low to high, because we will have it changes in the output. We may have it changes at the output at this point. And also we have a transition here. And finally a transition here. Okay. So let's do first AND. So during that time, or that duration, the input to the AND gate, the two inputs were both zeros. So the output should be 0. At that point, one of them become high, become 1. So from that location to that location, or that point to that point, X is always 1, Y is always 0. So basically, again, the output will be 0, because one of the conditions is not satisfied. As we said, both should be true, or 1, to have an output of 1. Now, from that point to that point, both are 1, so the output is 1. And again, from that point to that point, one of the input is 0, so we have 0. Then we have, again, 0 at the end, because both are zeros. How about OR? From that point to that point, both are zeros, so 0 or 0 is 0. Then 1 or 0 is 1. Then 1 or 1 is 1, not 2. It's not a plus. It's not an arithmetic plus. 0 or 1 is 1. 0 or 0 is 0. Finally, the note is very simple. So note here is not for X. Okay? So it has input, which is X. So 0 is input, 1 is output, because it's inverting, complementing, flipping. 1 is input, 0 is output. 1 is input, 0 is output. 0 is input, 1 is output. 0 is input, 1 is output. Okay? So basically, I'm saying here is that since we know that we get to realize that these inputs are just voltages, signals, something that is changing between two distinct values, zeros, high and low voltages. Then it is something like this. You know, if you have a oscilloscope and you put this wire into this oscilloscope to measure its voltage, you will see something like this. Okay. We all the time see it in this moment, you know, the AND and the OR has only two inputs. But can we have AND and OR gates with more than two inputs? Yes, we can have. But why we can have this? So basically, AND and OR are mathematical definitions. You know, this is something to realize or to model the human thinking or the human logic. Okay, if you have operation, this operation has two, for example, two conditions. Then, for example, for AND, both conditions should be satisfied in order to do this operation. Okay. And we get to realize that, or we, you know, recently in the last century, that we can have a circuit that has two inputs, and these two, and the output should be, you know, model or very similar to the AND logic. When both inputs are ones or high voltages, then we will see high voltage at the output. Okay. So basically, we can extend the mathematical, you know, the mathematical definition that you have operation. This operation, for example, has three conditions now. And all the conditions should be satisfied in order to get or order to do the operation. So all of them should be true so that you can have the output, so you can do the operation, or the output should be true. Okay, so easily you can extend the definition, the mathematical definition. Then we did, you know, or we invent a circuit that has three input voltages, A and B and C, for example, or X, Y, and Z. Okay, and the output voltage become only high when both A and B and C input voltages are high. Otherwise, it's zero. So since we could invent such a circuit, we could also use on, you know, adopt AND gates with multiple inputs. Okay, and the definition will be the same as I said. So let's do, and of course for OR we have also the same situation. So let's now do it. Okay. Basically, I'm saying for the AND, all the conditions should be satisfied in order to get, you know, in order to execute the output, or I'm sorry, to do the operation in the output, or to make the output true. So all the conditions here are not satisfied. So the output is zero. Again, the output is zero. Output is zero. Output is zero, because not all of them are satisfied. One of them here is not satisfied. Again, zero. Again, zero. Again, zero. And finally, all are satisfied. Then we put the output through, or we can do the operation. Okay. I forgot to say that another symbol that we use to make the AND is ampersand. This sign here. So we have three now. We can just put a period between the symbol or this ampersand, or you can just put nothing or nothing. This is for the AND operation. Okay. Good. For the OR, we can also extend the definition. Okay. So if you have n inputs, not just the three, if only one of them is satisfied, then you can do the operation. Otherwise, not. And this otherwise situation is that first one, in which all of them are not satisfied. So the output is zero. So here one of them satisfied, that's good. Another one satisfied. Here two satisfied, you know, more than good. You know, again, one satisfied, two satisfied, two satisfied. All of them are satisfied, excellent. Then the output is true. And also I forgot to say that another symbol for the OR is that bar here. Okay, so for the OR, we have the plus operation, or the plus sign. we have this bar, and yeah, we have also I'm sorry, we have just this plus sign, and we should do something. I mean, it's not like and you can just remove any symbol and that's it. Okay. One thing here is that why the invent or the adopt the dot or the period here as a symbol for the and is that it's like product, because 0 multiplied by anything will give you 0. Okay, so it has this similarity to the multiplication. 0 multiplied by anything will give you 0. So you can see this clearly here in all these situations. Okay, even if you have 1 million input and just one of them is 0, then if you multiply this 0 by 1 1 1 1 whatever, it will give you 0 at the end. Okay, good. One last thing here, another two important logic gates, okay, but they are derived from and or, which is the NAND, and the other one is called NOR. So this is the NAND, and this is the NOR. And actually, NAND is abbreviation for something, which is not AND. If you look here, you will find that this is actually an AND gate. This is an AND gate. Same symbol. Then we put this circle here. This circle is usually used for to express the inversion or negate operation, like the inverter. So if you notice in the inverter has such circle here at the output. Okay, and again, this is not or, so this is not and. And this is not or. So this is the symbol of or. Then we put, such a circle again. Okay. So let's do the truth table together. It's very simple. And I want to teach you here how to fill out the truth table. It's very simple. So you have here 3 inputs, A, B, and C. So you have 8 combinations, 2 to the power of 3. Each input has 2 distinct values, 0 or 1, because it's a binary variable. And you have 3 inputs, so you have 8 possible combinations, 2 to the power of 3. 2 to the power of 3, which is 8. Okay, how to fill the table? This is very simple. So you start by half of 8 as 0, then the other half are ones. For B, 0 0 1 1 0 0 1 1. So we start by 4 and 4, then 2 by 2, then 2 by 2, then 1 by 1. So 0 1 0 1 0 1 0 1. And again is in here. So here we will fill the NAND. Here we will fill the NOR. Again 0 0 0 0 1 1 1 1, then 0 0 1 1 0 0 1 1, then 0 1 0 1 0 1 0 1. Okay, good. So we want NAND, right? So let's do AND then negate it. So the AND here is 0 because all of them are not satisfied. Here one of them only is satisfied, so that's not enough. Again, one is not satisfied, not enough, not enough, not enough. Then here all of them are satisfied, this is enough. So we have an output of true or 1. Now for the NAND, we should just negate this. So 0 will become 1, 0 will become 1, 1, 1, 1, 1, 1, then 0 in that case. Okay, how about NOR? So let's do OR, then negate it. So all of them are not satisfied, so the output is not satisfied. Then here is 1, 1, 1, 1, 1, 1, 1. Then negate that, so 1, 0, 0, 0, 0, 0, 0, 1. Okay, so this is the NOR gate. Okay, guys, so this is the end of chapter 1. Okay, we have covered now. We make a quick revision for the definitions that we knew in our prerequisite course, digital circuits or digital circuits. Then we knew the basic, logic gates that we're gonna deal with in that course as well. Okay, which is AND, OR, and NOT, and derived from them NAND and NOR. Okay, so see you next week in chapter 2. Bye bye.